Geller, and today I'm going to be talking about solving query performance problems. It's management's desire very often for any DBA in the organization to be able to solve any problem. And they'll ask the senior DBA to create a checklist of steps to take to figure out what's wrong and how to solve it. Can this be done? Well, the short answer is no. It's just not enough. A simple flow chart is a little bit better, but still not good enough. I'm going to be presenting a rules-based approach with detailed rules that tell you what to look for, and based on what you found so far, what else to look for, how to put those clues together and lead to possible solutions. Query tuning is actually a lot like detective work. You examine the evidence, you search for clues, you create a hypothesis, and then you try to prove it. Now, I'm not going to be taking any questions during the session today because this is pre-recorded. However, there will be a live Q&A on August 13th at 2:15 in virtual room 3. So we're going to look at the whereabouts of all the evidence, the relationships between different pieces of evidence, and how one clue guides you to a different piece of the puzzle, and the relationships between clues and solutions. We'll learn what makes a good access path and how to achieve one, and hopefully come away with a checklist to guide you. There are two audiences for this presentation. Experienced DBAs and query tuners. I'm going to be presenting a lot of specific rules on items to examine and actions to take. But it's also geared to the inexperienced DBA or developer who wants to learn how to solve performance problems. And so there will also be general rules on how to approach the problem. I'll then be illustrating the rules with some real-world examples that I've come upon. Following that, there's an appendix with the complete list of rules, both what I cover in the session, plus a lot of others. There are two parts to the process. You have to find out what's wrong, what's causing the problem, and then figure out what is the solution. And in addition to the rules, it also helps to have knowledge, experience, and insight. Knowledge of the tables and indexes that your application has, knowledge of what DB2 does, how it determines an access path, how it processes a query. You can solve problems even with limited experience by following the rules, but knowing those things speeds the process along. Rule number 1, there are no rules. Well, that's not true. Of course there are rules. What this means is that there are so many combinations of evidence, metrics, access paths, statistics, so many different table and index designs and coding choices that there are often many different causes of problems and many possible solutions. Your tables are unique from his tables, and his are unique from her tables. The access patterns are different. The coding choices are different. You'll often see the same types of problems reoccurring in your shop, but sometimes you'll see things that are completely different. So you have to approach each problem as though they are different, and each analysis is different. Rule number 2, do not make assumptions. There's a difference between a hypothesis and an assumption. A hypothesis is a possibility that you've thought of, and then you set out to test it and prove it. An assumption is something you accept as true without any evidence or proof. Another word for that is don't take someone's word for what has occurred. Look at it with your own eyes. Ask questions. Is it online or batch? Because a good access path for online may not be for batch and vice versa. Does the problem happen with every occurrence of that stored program or just some? When do the bad ones happen? What do they have in common that are different from the good ones? It could be one flow in the program based on input data or data read, or it could be data related. One customer could have hundreds of orders and another just a few. And it's often useful to have a very fine granularity of metrics, even every minute, as opposed to 15-minute intervals or hourly intervals, because problems often happen just for a very short period. Is it production or test? Well, the first thing that tells you if it's production, you have to give it top priority and get right to it. If it's test, well, if you're busy with other important things, it can wait a little bit. When did it start? Are all programs affected or just one or a few? If all programs are affected, then it could be system related, an overloaded CPU or I/O system or the network, or there's something unusual running that's chewing up the resources. If it's one program, then which statement within it? You need breakdown of metrics by statement. What has changed? Of course you ask that, but usually the answer is nothing has changed. Right. The changes could be DB2 related, the program, the indexes, the statistics, or the data. Maybe there was a data migration and the volume of data has increased, or the values being used have changed. A function that was previously deployed but not in use yet may have been turned on, so it's something new. But it's not just what has changed in the DB2 code. It could be the front-end code, time spent outside of DB2. The front-end program could have a problem, or it could be calling a different DB2 program than it used to, or calling it more frequently, or passing different params. The data may have changed. There could be a higher volume of transactions, so more load on the system, more chance of contention. Data migration may have greatly increased the size of the tables. A large amount of updates may have increased the row size, and if there's no room on the pages, that leads to overflow records. And overflow is the term in LUW, and indirect reference, especially far indirect reference on ZOS. And it's where the row is moved to a different page with an anchor left where it was before. That way DB2 doesn't have to also update the indexes at that time. But this affects performance, especially batch performance. How slow is slow? How long does it run? How long does it usually take? Is it online versus batch? 10 seconds is slow for online, but it's fast for batch. If you've identified the statement with the problem, check the explain carefully. Even if the access path is not changed, look for anything that looks like it could be a problem if the statistics are not accurate. Look at the metrics. Identify where the time is being spent. Is it I/O time, CPU time, lock wait? If it's high CPU, look at the rows read and the logical reads. And on ZOS, logical reads are called get pages. If you have a batch program that has to read most of the table, a large table, then it's not necessarily a problem that the rows read is very high. But if it's inordinately high, then that's a sign of a bad access path. You're looking for the clues and tying them together, so you have to look at many things at once, switching from one kind of evidence to another and back again until you see the connections and how they're related to each other. At the same time as the metrics and explain, you have to look at the indexes and tables and the predicates and the statistics. The statement itself should be looked at to see what it's trying to do. The statistics are in the DB2 catalog as of the last time RunStats was run. You also often need to look at the actual statistics. What does the data look like right now? You have to get counts, row counts, distribution stats. If the current data doesn't match the catalog statistics, you have to see when RunStats was run. It could be out of date. And maybe you haven't collected distribution stats or column groups, but maybe you need them. Filter factors are, every predicate has an associated filter factor that DB2 estimates based on the statistics in the catalog. And this is the key to understanding the access path that DB2 has chosen, why it chose it, and how to solve the problem if it is a bad access path. The best source for learning about filter factors is a presentation I did at IDUG EMEA 2016, the ABCs of filter factors, also known as selectivity. And this presentation is available on the IDUG website, and you can watch it on YouTube or on 24, and this is the URL for it. So if you're really serious about learning how to tune performance problems, you have to watch this presentation. I think it's good. Rule 5, don't rule out DB2 bugs. I've gone several years without running into a performance-related bug, but sometimes I've hit several bugs in a very short period of time. Now, we don't have time to go over those today. However, all the details of these 3 examples are in the notes page. They're there for your reading pleasure. And of course, it might not be a bug. It's just as likely that I just don't fully understand what DB2 is doing. But either way, if it looks strange and I can't find another reason for it, it's time to ask IBM. Always save the production explain. Always look at the explain and check to see if there's any change. If a code change or a rebind has happened, you have to compare the previous production access path to what you have now. If the problem is a test environment, compare it to the production access path. And at the same time, look at the performance metrics. The approach is nonlinear. You look at the evidence, put the clues together, and apply your knowledge and experience. Not only can a rule trigger multiple actions, but you also have to return repeatedly to the things you've already looked at, because as you gather new clues, you have to see if that changes what you think about the other evidence that you've looked at. You have to multitask and pursue multiple threads at once. Now, you say you only have 1 CPU core up there. Well, there was a time when all computers only had 1 core, but there was concurrent processing. If one thread stops to do something like an I/O, the CPU was given over to another process. And besides, the brain is a neural network. It's capable of doing many things at once. Rule number 9, a key rule. First find the cause and then find a solution. Spending the time to identify the causes is more important than starting out testing out solutions. You may think that finding the solution is more important, but if you don't know the cause, then you're just guessing. If you know the cause, it'll guide you to the solutions. And of course, sometimes you don't have time to find the cause. If you have a problem that must be fixed now, and it turns out it's an access path problem, if you can revert back to the old access path. If you're on ZOS and you're using access path stability, switching to the old one is easy. But since you know what the old access path was, you can use an access path hint to get back the old access path. And that's still a pretty quick fix. Don't rule out database design, poor database design. You really don't want that to be the cause of your problems because it's much harder to fix and change than the other solutions. But often Bad design can cause performance problems that affect multiple queries. There are two pillars to your analysis: the access path and the metrics. You have to see if the access path looks good, and the metrics help you pinpoint which statement's causing the problem and where the time is being spent. Always have the explain to look at, always check the metrics, look at the indexes. You have to know what exists so that you can make a determination whether you think the chosen index was a good access path, or maybe there's a better index that DB2 should have used, in your opinion. Check the stats. Are they comprehensive and are they current? Look at the query itself. It could be written poorly from a performance aspect. It could even have bugs in it. That's especially true in a development environment, but from time to time, bugs turn up in production also. Now we'll start looking at specific rules. I've grouped the rules into categories. So there are access path rules, run stats rules, reorg rules, and then I number them within each category. So we're going to look at one particular access path rule related to nested loop joins. If the right-hand side, which is the inner table, returns many, many rows for each row on the left-hand side, or if the estimated cost is extremely high, then there's likely to be something wrong with this access path. Another way to spot this is if the access to the inner table is a table scan or an index scan with no matching predicates. If those are the cases, you've got a problem. Check the code. Make sure there are join predicates. Otherwise, it's a Cartesian product, joining every outer row to every inner row. If there is an index to be used and there are join predicates, see why effective index access is not being done. Check for compatible data types and make sure the join column of the inner table doesn't have an expression or function on it, because those prevent index access on that column. Check the index that's being used, make sure that there is one on the join columns. If there's no good index on the join columns, then why didn't DB2 pick a merge scan join or a hash join? Again, check for compatible data types and make sure there's no function being used on the column. Should there be a new index if there isn't a good one? Well, before you do that, read the rules on indexes and read the presentations from Martin Hubel and others on why adding a new index is not your first choice of solution. Too many indexes are bad for overall performance. So if you have another solution that doesn't require adding a new index, then that's definitely preferred. If there is a good index, but the predicate's not indexable, fix the code. Put in the join predicates if they're missing. Rewrite the predicate to enable index access. That's rule IX4. If the columns are just incompatible, we'll check with the business analyst and the dev team to see what the table design is and the functionality and why you have related tables that don't match up well. If another join method would be better, merge scan and hash join are good for batch programs that process a large percentage of the tables. Well, then why did DB2 choose nested loop? Make sure the statistics are accurate. If they're out of date, do run stats and rebind. Did you collect all the stats that you need? If the filter factors are not accurate, and if you can't easily collect the right statistics, for example, if there are host variables being used and DB2 just doesn't know what value is being used, consider selectivity overrides or access path hints. On ZOS, both of those are stored in the access path repository. On LUW, you can put selectivity overrides and opt guidelines directly in your program right along with the query. Make sure that the access path, if the access path and the statistics and the filter factors look good to you, then look at the performance metrics. Now, sometimes you might start with the metrics. If a performance problem is reported, either you're not told which program, and you have to identify which program is the problem, or it happens, you are told that there's a particular program, but it could be the victim of another program. So you may not know which transaction or program is slow, and you need to identify which statements are taking too long. If the number of executions is too high for what you would expect, maybe there's a program loop that's executing, that's doing more than it should. Check the elapsed time. You have to identify which statements are taking the most time, and especially if they stand out as being much higher than the rest. And there are actually two types of elapsed time. There's the time spent by this statement and everything it invokes. And there's the time spent just in this statement alone, not counting the things that it invokes. So an example of the first kind is a call statement. The call itself doesn't take long, but the stored procedure might. So you need to drill down to find out which statements are actually doing the work. A UDF invoked as part of the statement is another example. The time reported just for this statement alone is where you'll find out exactly where the time is being spent. For each high elapsed time statement, you have to find out which metric is high, I/O, lock weight, CPU, and you should compare it to the metrics from a previously good period to see which one has increased. It might be high, but maybe it was always high. Maybe a different metric is now the one that's increased a lot. If it's the I/O time, the read time that's very high, you need to check the number of logical and physical reads, which on ZOS are get pages and I/Os, or synchronous reads. The hit ratio is not where you start. First off, a ratio is not a measurement of time. It's the actual number of physical I/Os that are what take the time. And sometimes I/Os per second is useful, but you need to start with how many actual I/Os occurred for this transaction. Then, if it's very high, the hit ratio can help you figure out what's wrong. What DB2 does when it needs a row is it goes to the page that it needs. First, it looks in the buffer pool, which is a memory area where it's stored pages that it's already read recently. And if that buffer pool is too small, then you may have a lot more I/O than you should. If the access is random access jumping around a very large table, you're also going to get a very low hit ratio. If the hit ratio is good, then check the logical reads. Because maybe the physical reads are high, but the logical reads are very, very high. So it could be an access path problem that's causing DB2 to read too many rows. If the read time is very high for the number of physical reads, then there could be something wrong with the I/O system. And this would likely mean that other queries are also slow. If the access path uses prefetch, now, prefetch is an access path when DB2 has to do a table scan or an index scan reading a lot of rows. It will use prefetch of one type or another, and that means it's going to read a lot of pages with a single I/O, and it's going to do it asynchronously. It'll issue this I/O before it's up to that set of data, while it's still processing the previous set of pages that it's read. But if it's using prefetch and you still see a lot of logical and physical reads, then that may be a sign that there are a lot of indirect references or overflows. If the CPU time is very high, check the number of rows read and number of logical reads or get pages, and check the access path. Reading rows and examining pages uses a lot of CPU time. And if the same rows are being read repeatedly, then it's likely they're in the buffer pool after the first time they're read. So the I/O time may be low, but the CPU time could be very high, like the example we just showed with the table scan of the inner table of a nested loop join. If there's a lot of time being spent waiting for locks, you have to see exactly what you're waiting on, who the holder of that lock is. You may need to look at the whole application flow because there may be multiple things happening that are causing rows to be locked in one flow and another flow is trying to read them. You're going to look to see if there are any long-running units of work that are not doing frequent commits and are holding locks for much longer than they should be. And sometimes there are stale connections. A program will finish but not do a commit or terminate the connection. Something went wrong in the front end and it just didn't finish. So those locks are being held for a very long time. It could be a multi-threaded batch job and maybe even doing concurrent update of the same row. Also, low cardinality indexes can cause lock wait issues. A low cardinality index, such as one on status or order type, can cause all kinds of problems, including lock wait problems. So what happens is you have many, many rows that have the same value. So for DB2 to find the right entry to update, if you're doing an update of status, or you're inserting rows and it has to find the right place in that chain of rows entries, it's going to take a lot of time. So it's much better to have indexes with higher cardinality, more different index entries. And if you want to have an index starting with status, that's fine, but it's good to have other columns in that index too, either the key to the row, the primary key, or maybe other columns that are used in predicates frequently. You have to ask, is it just the one query or is everything slow? Rule 5, if the CPU time is very high, then rule 6, check the wait time. Rule 7, if it's only the CPU that's high, check the rows read. And if the rows read is very high, check the logical reads or get pages because that's corroborating evidence. In this case, suspect that there are many scans of the same set of data and look at the explain and so on. So as you can see, each rule can tell you something to look for or point you to another rule to look for something and possibly lead to various other actions. The buffer pools. If the I/O time is high, then check the number of physical reads and for which component. Different performance monitors give different breakdowns of data. If you've got one that can break it down by data and index and temp space, or even better by individual table, then that's great. Check the hit ratio. If it's too low, check the size of the buffer pools. A mature, well-running database is likely to have well-sized buffer pools, but if it's a new database or a test database, then it's possible the buffer pools were never sized properly. But even if the buffer pools as a whole are big enough, it's possible that a new table space is created and assigned to a buffer pool that's not one of the well-sized ones. And don't forget, if the database was just recycled, the buffer pools are going to start off empty. So you're going to get a lot more I/O than normal at first. If the buffer pools are okay, then rule IX9, check which index is being used and its cluster ratio. If the cluster ratio is low, well, the symptom is you're going to have a lot of random access to different pages. So you want to check IX10 if it is the clustering index, but the cluster ratio is low, then a reorg of the table will certainly help. If it's not the clustering index, then check your usage of your different indexes to see if the right index has been chosen to be the clustering index. Often the primary key is just a system-generated number, and you're not reading a set of rows for the same value or similar values of that key. And it might be better to have a business key as the clustering index. Check the rows read and rows return. If for the predicates on the key columns, you have a very high number of rows read, for example, if you have an index on cust ID and you're getting all the orders for that customer, but you have further filtering on other predicates that are in the row, and the symptom of that is that the rows returned from that node is much smaller than the rows read. Consider adding those columns with predicates to the index so that more will be filtered when processing the index entries, and put them in the order they're most likely to be used in predicates. And this is especially true if it's something that happens in more than one program. For example, with the orders, besides the customer, you may often have predicates on order status. I only want the open ones, or the ones that were delivered, or the order date. Give me the ones ordered in the last week. So adding those to the index will filter the index entries, and you can eliminate the I/O and avoid it on the data rows. If there are no other predicates on the columns in the index, then see if maybe you could add some. For example, if you have a query that returns all claims for a customer, well, maybe you could also limit it to just a date range. So perhaps defaulting to just getting the last 3 months. And if the customer wants more, he can ask for it. Query rewrite rules. You can often rewrite the query, sometimes in very simple ways, that can greatly improve the performance. And you used to originally have to do all this query rewrite yourself, but nowadays DB2 will do a lot of it for you. Now, one symptom is you may see predicates that you think should be in one node early in the access path, but DB2 only has them later on in the access path. Or maybe you think the filtering should be in more than one place. Well, one of the things that could be helpful is predicate transitive closure, which we'll talk about on the next slide. And there are also transformations to eliminate expressions on index columns to make more predicates indexable. And then if you have subqueries, and you or DB2 can transform correlated subqueries, non-correlated subqueries, and joins from one to the other. And DB2 will do that to what it thinks will give it the most choices of access path. And if DB2 doesn't do it, you can do it and try it out. Transitive closure means that if you have two predicates, A equals B and B equals C, that implies that A will equal C. So if you have table 1 and table 2 and the join column has, one of them has a predicate, that column equals 0. Well, if you're joining them on the key columns, that implies that that column in table 2 would also equal 0. And why does it matter? Well, because when you're joining, generally DB2 will pick to be the first table in the join, the one with the lower cardinality after applying filtering. If you have the predicate on both key columns, that'll give DB2 more choices, and it'll be able to do filtering sooner. Well, how do you know if DB2 did it for you? You look at the visual explain. The optimized query will sometimes show the added predicates, but sometimes not. But if you check the node for that index access or table fetch access, you can check the predicates to see if it's been added. And if it hasn't, you can add it yourself. Now, with each release of DB2, it's being done for more cases. The first thing it was done for was equal predicates. Then ranges were added, but not all the time. It won't do it if it's in the tables or in different query blocks. If you have an expression on the column, DB2 will sometimes rewrite it to not use an expression, and then transitive closure can be done. But if DB2 has not rewritten it, it cannot do transitive closure if there's an expression. Now, what kind of expressions will DB2 rewrite? Well, one example is if you have year of a date column equal to YYYY, that can get rewritten as date column is greater than January or equal to January 1st of that year and less than or equal to December 31st. However, it only does it for the year of the date column. If your predicate was on the month, I want to find things just that happened in February, then DB2 will not transform it. And if you have a predicate on due date on table A, DB2 will not add the predicate on month of B.due date equal to 11. And again, you could add that predicate yourself if it'll help. Query rewrite rule 1. You have predicates on the index columns, but match cols equals 0, which on LUW is called start and stop keys. Then you want to check, is there an expression on the column? Are you comparing different data types? Originally, DB2 was a strongly typed language. You could not mix literal or variables of numeric data type with ones that were strings or character variables or literals. But now DB2 can do implicit conversions. However, it does that by using functions, built-in functions. And if it uses it on the side with a column of an index, using that column would make it non-indexable, that predicate. And so if you find that, what you can do, well, the first thing you can do is avoid the problem if you can. If you're using literals, don't mix numbers and string literals. If it's supposed to be a number, leave out those quote marks. But if it's variable columns that are being compared and they're different data types, then what you can do is you can explicitly do the cast on the column that's not the one in the index you want to use. So you're going to reverse which side of that comparison of the predicate that conversion is being done on. And what you have to do is look at the explain to find that that's what has occurred, that implicit cast. And sometimes you can just add additional predicates to filter more rows. Maybe if the order type is this, then there'll be some other column which has to be something. And you could or maybe it's in a different table that would have a similar type of column, and you can add that predicate and get additional filtering sooner. If there's no appropriate index, rewrite the query if you can, create a new index if it's appropriate, or modify an existing index to add more columns. If it's a batch query, well, maybe it doesn't pay to create a new index, just force a merge scan or hash join. That may be even more appropriate for the batch query. If the problem's in a non-production environment, then suspect everything. The index definitions could be wrong. The stats could be out of date. The memory areas like buffer pools are likely to be undersized, and it's more likely that the program code is going to have bugs. Run stats rules, well, we already went over some of these. Make sure they're good and thorough. Check the stats time. If the data has changed a lot, consider run stats. Make sure that the stats time for the indexes and the tables are all in sync with each other and were not collected at different times. Make sure you've got good index cardinality stats for all the key columns, and check the filter factors. One thing to check for is see if a default filter factor is being used. If DB2 doesn't have enough information, it cannot calculate a good filter factor. For example, if you have column equal variable, and you know that the cardinality, the number of rows of different columns, values there are for that column, then the filter factor will be 1 divided by the column cardinality. But if there's an expression on that column, then DB2 can't use that information, and it'll use the default. The same is true of distribution stats. DB2 cannot use them if you're using a variable. Well, how do you know that there's a default filter factor? Well, the default for column cardinality is 25 different values. So column equal variable would have a default filter factor of 0.04. So if you see a filter factor of 0.04, check to make sure you've got column cardinality stats and look to see if you have an expression on the column, because both of those will lead to the default. And don't forget to check for implicit casting or other DB2 query rewrite. So if a column has uniform distribution, then you don't need distribution statistics. But if it does have data skew, like most rows have a status of completed, a small number are active. The order types, some are used very frequently and some infrequently. If the stats that you see from the catalog are way different than the actual data, then make sure the stats are not old and run stats. So you need to get the row counts and the counts by value. If there is data skew, and you have to look at the predicates that are using it and compare it to the actual data, that filter factor. If the predicate is using a variable instead of a literal, find out what values are being used. If you have distribution stats and a literal is used, then if there's only one value being used by that program, consider changing the code to use that literal. If there's skew and a variable is being used, but there's more than one value that's used, you could try breaking up the query into separate selects with literals, or you could use reopt bind option or dynamic SQL. And if you don't have the distribution stats and you're using literals, then you have to collect them. It's not uncommon for a developer to ask the DBA to run a reorg because they have a performance problem. But in most cases, that's not the solution. And rather than wasting time and resources just reorging, first determine if there is a need for a reorg, if it's even a possibility. And the rules will tell you what clues to look for to make that determination. But here are some guidelines. Rule of thumb, if performance has gotten much worse suddenly, it's very unlikely due to needing a reorg, especially if it's only affecting one program rather than many. But it's not impossible. If the data was previously clustered by the primary key, and you've just done a load replace and you didn't sort the input by that key, then now the data is very unclustered, and there could be a significant increase in random I/O. On the other hand, if performance has been gradually increasing and it affects multiple programs, two possibilities are likely. If there's a decrease in clustering because of the cluster ratio getting lower, or there's an increase in indirect references, then that's a signal that a reorg would help. On the other hand, if there's been a large increase in data volume, either total number of rows or the number of rows per parent, such as a large increase in the number of orders per customer, and you can check this by looking at the rows read or the get pages. If it's index-only access, you won't have rows read, so you want to look at the get pages and compare it to a previous time. In this case, a reorg is probably not the solution. First, you have to talk to the dev team and business team to find out why there's an increase. One possibility is that there's more business, and that's a good thing. Or maybe they've turned on something or done a migration, or maybe there was a mistake made. Anything is possible. Now, possible solutions are to archive or purge the older data if it's no longer needed. And archiving or purging should happen on a regular basis. Or it could be an access path problem where it's looking at more data initially and it's being filtered later. Maybe there's a way to improve that. We're going to skip the database design rules for now. And we're going to go to some examples. These are the problems that I've had. The first one, we had a transaction, a stored procedure whose elapsed time went from 50 milliseconds to hundreds of milliseconds. And this was a very high transaction volume. So that's important and significant. There were 30 statements in the stored procedure. So the first thing we had to do was look at the metrics to pinpoint which statements or statements were the issue. Comparing to the metrics from a prior period, I could see that normally there were 4 or 5 statements that were the most costly. But today there was a different one at the top and by quite a bit. So I looked at the metrics to see which thing increased. And in this case, it was all CPU time. So metric rule 9, if the CPU time is high, check the rows read and look at the explain. And check to see if the program has changed or the access path has changed. And in this case, there was no change to the program or the access path in a long time. Rule 12. We're taking a brief pause now to examine the suspects. Rule 12. If only one query is affected, suspect the access path. Rule 13. If the code or statistics have changed, the access path is your prime suspect. Rule 14. But if the code and statistics have not changed, suspect the data. Rule 15. There can be more than one criminal. They can be working together to commit the crime. Here is a simplified version of the query. We're joining 3 tables, 2 mapping tables and a third table, joining by the key columns, and there's a predicate on the key column of the first table. The access path is doing index access for each table, and it's using the primary key all the way through. What could be wrong with that? Take a look for a minute and see if you can spot what looks funny. Well, that first table has 0 rows, the first table in the access path, and that's always suspicious. Look at the code. There are no local predicates on that table. Look at the access path. Look at the details, and that index scan has no predicates. This is not a good access path, even though it's an index. It's a full scan of the index with no predicates. But DB2 can process nothing very quickly. Well, let's go back to rule 3. What has changed? I called the lead developer and asked, how many rows does the table have? 15. When did it start getting rows? Last week. Ah, something did change. Using the monitoring data, I could see that the elapsed time was increasing during the last week, and it just reached problem level this morning. And all that increase was CPU time. But the first table is small, only 500 rows, and the other 2 are using the primary key, one for the second table and one for the third. Doesn't sound like a problem, but let's add that up. 500 index accesses for the first table, and 500 index accesses and rows read for the second and third table. So for every call, DB2 had to examine 1,000 rows and 1,500 index entries. And that's enough to cause that increase in CPU time. And no increase in I/O, because after they're read the first time, they're all in the buffer pool. So what's the solution? Well, similar queries with different tables that had statistics with rows on the lead column had an access path that started with that table and using that had the predicate on that first column of the primary key. So we want to do that for our query also. So I could use an access path hint, but a better solution is to get good statistics. Since there are only 500 rows and it's going to grow quite a bit, we loaded 200,000 rows in a test environment, ran run sets there, rebound, and checked the access path there. And then we copied the stats to production and rebound, and checked the access path to make sure it did change back, or change to what we wanted. And here's the access path now, starting with the table with the local predicate, doing the filtering, and then using the primary key to get to the other tables. Example 2, we had a performance test environment where the transaction is much slower than production, even though they have the same access path. In production, it takes less than 100 milliseconds. In the performance environment, it was taking 9 whole seconds. The production metrics showed an average of 40 rows read, but in performance, it was showing 20,000 rows read for the queries. Why? Well, the high performance test environment, including inserting many, many rows, but they weren't spreading it across as many customers as was typical in production. Not enough different customers, so the number of rows per customer was much higher. How do I confirm that? Because at that point, that was just my hypothesis based on the metrics. Confirm it with real statistics. You run queries with counts and group bys, such as select count of asterisk and cust ID, grouping by cust ID, having count of asterisk greater than 1,000. If the query has a number of possible indexes, that could be a data problem in a number of different places. So you have to check. And the solution, of course, was to get rid of all that excess data in the performance environment and to change their process to use more different customers. Example 3, we had an access path that switched from index access, and DB2's estimate was 1 1/3 rows per index entry, to list prefetch. Why? List prefetch makes no sense for 1 1/3 index entries. So what's new? There was new run stats run. So I examined the statistics closely. And what the distribution stats showed was that the most frequently occurring values had hundreds of rows. A host variable was used in the query, and DB2 didn't know if it's going to be hundreds, for which list prefetch might be better, or only 1 1/3. So what did we do? Don't rule out a bug. If it doesn't make sense to you, it could be a DB2 bug. First action, I opened the PMR. It could also mean I just don't know everything. Action 2, this was just 2 weeks before the IDUG conference, so I went and I asked John Hornibrook about it. John is the DB2 optimizer person on LUW, and he suggested a registry variable that says that the optimizer has trouble with parameter markers and list prefetch in cases like this. And this registry variable says, favor not using list prefetch. Example 4, we had a batch job that normally ran in a couple of hours, and suddenly it was running for 8 hours with no end in sight. They had to cancel the job. What's changed? Well, the tables of this query had run stats run on them for the first time since they were created 4 months prior, with run stats at that time, but not since. So we look at the explain in the metrics, and the access path had changed. This was on LUW, and it had been hash joins, which is good for batch, but now it was a nested loop join. So the two questions are, why did it change, and why is it so slow? Now, normally you want to first understand what's the problem and then find a solution, but this was production. We had to get it fixed fast, and therefore first. LUW does not have access path stability, but since we know what the old access path was, we could force it with an opt guideline, and that's what we did. We reran it, and it took 4 hours to completion. Great. But operations says it used to take 2 hours. So now I had to do more investigation. But looking at the past metrics, I saw that it actually had been growing over the last few months. It started at 2 hours, but had grown to 4 hours prior to the new run stats and access path change. So that 4 hours was actually correct. But we still would like to understand why it used to be 2 and get back to that. We also still want to know, why did the nested loop take so long? Well, it had extremely high I/O, synchronous reads. And looking at the statistics, we saw there were a bit more rows, but there was now a very high overflow count. And as I said, that's bad for batch. And the reason why is because for the table scan, DB2 is doing sequential prefetch, which, as I said, if the row is now larger after an update and doesn't fit, it'll move it to another page. And in batch, because it's asynchronous I/O, when DB2 hits that overflow anchor, it has to stop and go do a synchronous read to get the row itself. And the job was gradually increasing because over time there were more overflows. Why did the nested loop take so long? Because if a join is on 2 tables that are not clustered by the join columns, they're clustered differently, you're going to get a lot of synchronous random access. And these tables didn't have clustering indexes, but even if they did, it wouldn't have been the same key. And the metrics did show that the number of IOs was very, very, very high. Why did DB2 change to nested loop, since it was clearly much worse? Well, it turns out there was an optimizer bug that overestimated the cost of prefetch when there were a lot of overflows. What's the solution? Well, we need two solutions. Get rid of the overflows and get DB2 to pick the right access path without having to use hints. To get rid of overflows, do a reorg. We did that on all the tables and the job went back to 2 hours, and we scheduled regular reorgs from then on. If the overflows are high, to get DB2 to go back to the better access path, we need the stats to say that there are no overflows. So we could run stats right after the reorg, or we could manually update the catalog column to say there are no overflows. What's the best solution when there are choices? And here are a number of possible solutions to different problems. What does best mean? Well, fixing it fast is important. Least intrusive, that means a simpler change. No code change and no outage is really good. It works is certainly a good attribute. Works better. Visible. I like my hints to be inline in the code and not external. That way, when you have a different developer 2 years from now, he'll know that there is a hint existing for that query and that it won't come back to bite you. An access path switch may no longer apply next time you modify the query, and the same with an access path hint. So if you just revert the access path now, a year from now when you make a change, you may run into the same problem again and have to now figure out why and come up with a solution. The future. Is the set of rules complete? No. As I think of more things, I'll add more. And if in your outage analysis, you train your less experienced colleagues using this approach, I'd appreciate feedback to let me know if it's been helpful. As you come upon different analysis than I do, different problems, have different ideas on what's a good solution, feel free to add your own rules and customize it for yourself. And then there's automation. With a good extensible rules engine, you might be able to automate the flow and analysis. If a rule says check the metrics and look at the CPU, a module could be written to fire that rule, fire the appropriate query, return the metrics, compare to the predefined value threshold in the rule, and follow the actions. And then there's machine learning. Of course, everything is better by machine learning. With training, the machine learning could determine the best threshold to use for the rule. What does very high mean? And it could change over time. So the machine learning model could determine better thresholds and better rules that lead to solutions. And if you build automation or machine learning, you might have a potentially lucrative product, and I wouldn't mind if you'd share some of that profit with me. Now we come to the rules. So we have different categories. And as I said, it's the ones we went over, but it has all the rules I thought of. So now there are lots and lots of rules. And they're there so that you can look at them and see if there are any new ones for you to pick up good information, or ones to use for training your less experienced colleagues. And as I said, there will be a live Q&A on October 13th from 2:15 to 4:15 in virtual room 3. And live means that I will be there, and hopefully you will be there too. Thank you.